Okay, so this lecture is going to be about computational problems. Terms computation, and there are some problems. So computation as such is not like limited to computers. We all compute every day. Like kids compute how to straddle stairs. Then you might also compute mentally like what is the throw with which you have to throw a ball or things like that. So it's not really limited to computers, but computers aid us to perform computation. Right? They are devices that can be programmed to compute things we want them to compute. So what are some problems that we come across every day which are not particularly limited to computers but are computational in a certain sense? Okay. So let's start with some examples. So multiplication. So you're given two numbers A, B. Numbers A, B. Compute the product of A and B. So I'll just denote it by A times B. Right. So these numbers are possibly like n digit numbers. So that's a computational problem. Right. The input is two numbers A and B and the output is A times B, which is the product. Another problem is the problem of primes. So you're given a number and you want to test whether this number is prime or not. So given an n, so maybe I'll put n greater than or equal to 2, test if n is prime or not. So n is greater than or equal to 2, so every number is either prime or composite. So slightly more harder problem is the greatest common divisor. Okay. So given again you are given two numbers A, B. Let's say both the numbers are positive and again n digits or something like that. You want to compute the greatest common divisor of A and B. So you are all familiar with the greatest common divisor, right? So D is the GCD. If it divides A and it divides B, and for any other number that divides A and B, that number should divide D. Right? So that's the greatest common divisor. Okay, so something slightly more different. Okay. So odd cycle. So you're given a graph. Are you all familiar with graphs? Okay, so it's something like that, looks like this. It's a bunch of vertices and together with a set of edges. Right? So you are given a graph G. Test if G has an odd cycle. So what I mean by that is, does it have a cycle of length like 2k plus 1 for some k? Right? So this is a graph that has odd cycle. This is a graph that does not have an odd cycle. Right? So this, if I consider this is a yes answer and this is a no answer to the problem. A more harder problem is planarity. Okay. So have you heard of planar graphs? So a planar graph is a graph that you can draw on any plane without edges crossing. So this is an example of a planar graph. This is a planar graph. This doesn't quite look like a planar graph, but you can possibly like make it planar. It's the same thing, right? Drawn with one edge outside. This possibly, if you sit and try to draw it without edge crossings, you probably can't. Okay? So this is an example of a graph that cannot be drawn on a plane without any edge crossings. So here also you are given a graph G. Test if G is planar. So by the way, everything has or not. Okay, is this okay? So here is. So the problems are in the order of increasing difficulty for whatever that means. Right? We'll try to see what is difficult. And is it difficult for humans or computers and so on. Okay. So here again this is a problem where the input is a graph. So you are given a graph G. What do I want to do? I want to sort of partition these vertices into two sets. Right? Some of them may be like this, the other in a different set. such that if you look at edges with one endpoint here and the other endpoint in pink, the number of such edges should be maximized. So what do I mean by that? Right? Find a partition of the vertices, so two parts, okay, such that if I look at the number of edges UV with U in S, B in T, right? So this cardinality is maximized. So for example, if this is the graph, I can put this in S and the rest of them in T, right? All the other four vertices. But then there's only one edge here, right? But if I put all these vertices in S and this one alone in T, I would get all the edges with that property. Is that okay? So this is called a cut. So you are asked to maximize the cut. Okay, so here is one problem that you probably already saw in yesterday's lecture. So can you describe the problem? It was done yesterday.
I'm guessing you're talking about two set.
Okay.
So you have n expressions, let's say n expressions, and each of them has n variables. We will combine for each expression, it would be x1 or not x1 with the or symbol, with x2 state or x3 state up till xn state. There may be variables which are not present in the expression.
Okay.
And each expression is ANDed together, and we see if there is a setting for x1, x2 up till xn such that all of it is like the entire expression turns out to be true.
That's pretty much it, but I didn't get where the 2 came in from. But that's almost it, right? So you said 2 set. Nothing
because we'll be doing because this is like, I'm guessing this is for computable, so.
Okay, but we have not gotten to computability, right? Okay. So the input is a formula. So what do I mean by that? So I'm writing Boolean formula on a bunch of variables. Okay, so x1 to xn are the variables, and phi is the formula. Okay, and it can be in any form that he says. Probably and of ors or of ands. Right now I don't care about it, but it's some formula. So when I say Boolean formula, it's using like and, or, and not gates. It's a Boolean expression. Right? I want to decide if it is satisfiable. So what do I mean by that? So the question is, does there exist a setting of a1 to an? So x1 to xn I can substitute with a1 to an, where each ai is in 0, 1, such that the moment I plug in a1 to an, this formula is going to evaluate to true. Is that okay? Right. So a couple of more questions and then we'll. So maybe you may want to check that x1 and not x1, is it satisfiable? So which of this is satisfiable and which is unsatisfiable?
One is not satisfiable.
Right, the second one is, put 1, 1, 1, 0 and so. So here is a slightly different question of the same flavor. So if I actually look at this formula, there are several assignments that satisfy this formula, right? 1, 0, 0, 1, 1, 1, all of them, except one of them. Now I want you to count the number of such assignments. So it's the same thing. So given phi, right, count the number of satisfying assignments. So if the Boolean formula is on n variables, how many such assignments can be there? 2 power n, right? So the maximum value is 2 power n. So here is another version of that, which you probably saw yesterday, I guess, the satisfiability. So you're given a formula again. But suppose I also know that this formula is satisfiable. can you output that assignment which satisfies the formula, right? So given phi, so let's say it's satisfiable, search or output that satisfying assignment. Okay, so we saw some problems. So there are a couple of questions you should ask here, right? But you didn't. I said given, but nobody asked me how it is given, right? Every question has a given, right? So how is the number given? How are these graphs given to you, right? If you, right. So then what do you want to do? You want to sort of operate on the input, right? However it is given to you, depending on the format of the input. Okay, so that's one question. The other thing is these problems have a slightly different flavor. So this problem asks you to compute a quantity. This problem, third problem GCD, also asks you to compute an answer. Whereas these problems such as primes, odd cycle and planarity ask you to decide whether the input is a yes answer or a no answer. The sixth one is sort of even more complicated because there are several possible answers and you want to find one answer that maximizes that metric, right? Probably the minimum value, maximum value and so on. This again is like a decision problem. You're asking, is it satisfied? Is it yes, no? Right? The answer is yes or no. Satisfiable or not. This is a totally different thing, right? It's not even optimizing. It's asking you to output the count of all possible solutions that you can get. This is sort of different from the count. So I'm not asking you the count. I'm saying if there is one, just get me that one answer. Okay? So computational problems can be decision problems. So decision problem is where there is a decisive answer, yes or no. Right? So primes is an example. Planarity is an example. Or they can be search problems where you are like searching for an assignment. They can be counting problems where you have to count some, like the number of assignments and so on. Or if you have seen matchings in graphs, count the number of matchings and so on. Right? Or they could even be optimization problems. So this at the moment has nothing to do with like computers itself, right? I mean, it's just that something that you can sit down and work with, some mathematical problem. So now we need to see how to manipulate these using computers. That's where the given actually comes in, right? So how are you given and how do you want to produce an answer? Okay. So there are several ways to solve a given problem, right? This is true for any mathematical problem. Like you might come up with a solution that he might not come up with and so on. So there are several possible ways to solve a given problem. And this kind of a procedure to solve a particular problem is usually called an algorithm, which you have heard of. So it's a step-by-step procedure to solve a problem. Which in principle should be programmable. Right? In the end, you want to program that algorithm. So now, then what do we want, right? You come up with an algorithm, somebody else comes up with a different algorithm. How do I say that one algorithm is better than the other person's algorithm? There should be some way to compare these algorithms, right? So first we need to see how is the input given. So let's look at some basic problem, one of the problems that we saw today, which is primes. So the problem is you are given n and you want to decide whether it is prime or not. Okay. So what is the first algorithm that you would probably come up with? 2 to square root n. Is there any factor? Right? You can run over all numbers from 2 for all a. 2 to root n. You want to sort of test if a divides n. So how long does it take? When I mean how long, how many steps does it take? Let's say that every step is like unit cost. Testing a divides n is like unit cost. Root n. So number of steps is root n. So when I say given n, right, if n is given in binary, how many bits do you need to represent this number n? Log n bits. So then how does the number of steps depend on the input representation? Okay, this appears to be exponential in the input representation. Right, so if you really draw the curve, right, it just shoots up. As x increases, 2 power x will be much larger. Right? So I might want to compare 2 power x versus x power 100, let's see. This quantity is going to be certainly better than this, right, for smaller like x, right, as x increases, this increases much slower compared to the rate at which 2 power x increases, right. So if your algorithm takes 2 power x time, where x is the size of the input, right, then it's not a very good algorithm in practice. Right. So you should look at how the input is presented to you and try to devise an algorithm that runs fast in terms of the input size. Right? So because we want to talk about binary at least. Is it clear that this is not a really good algorithm when the input is presented in binary? Right? Okay. So exponential running time versus poly runtimes. There is usually a trade-off, like some exponential algorithms are considered to be like not so good, but poly runtimes are really the good estimates that you should attack. Okay. So if several of you come up with several algorithms for testing whether a number is prime or not, the one that I would pick would be a one that runs in time polynomial in the input size. Okay. So let's write that down. An algorithm is said to be efficient if it runs in time polynomial in the input. So this algorithm is said to run in time poly in, like, say, the length of the input x for all inputs. So no matter what the input is, right, the run time should be polynomial in the length of the input. So if the input is given in binary, then an ideal algorithm for primes would be something that runs in like some a times log n to the c, right? So polylogarithmic, not a running time of root n or so. Is that okay? Oh. So now let's move on to. So amongst the problems, amongst the many problems here, some of them have polynomial such efficient algorithms. For example, multiplication. Right? This you would have done in school. Has. At least primes, immediately it is not clear if it has. The algorithm that you all came up with really does not have, runs in time root n. Right? So it's not a priori clear if this problem can be efficiently solved. Probably there is something that we don't know. Right? That's but the straightforward algorithm does not work. GCD, maybe you should go back and check. So what is a usual procedure to do GCD? Euclid's algorithm. So maybe you can go back and check, right? What is the number of steps this algorithm takes?
Log n.
Yeah, but you have to formally prove it.
Yeah, if Fibonacci sequence is the worst set of numbers.
That is true, but Fibonacci sequence is the worst case is also something that we should like prove. Yeah, so if you formally prove all that, yes, it is, right? How these, so that given AB, the given really is important. How is the input given to you? Maybe you can go back and check odd cycle. This one is sort of hard, planarity. The others, at the moment I am not able to say, just by looking at the problem, I am unable to say whether it is easy or hard to solve. Okay. So what about satisfiability? Sorry?
Depends on n.
Okay, so what do you mean by satisfiability? Okay, so maybe I should write this here. So no matter what the input is, it should run in time polynomial in that input. Right? That's what we mean by efficient. So if you give me, so there is another thing that you never asked me. When I said given a Boolean formula, how is the Boolean formula given to you?
The standard way, I guess.
What is the standard way to give a Boolean formula?
The one I described earlier, in which there are expressions which are joined by and each expression is joined by ors and nots of each x.
Okay. So we'll get to that. Okay. So before that, there is something that I should say. So there are amongst problems, let's look at decision problems. Okay. So problems that have yes, no answer. So decision problems. Oops. So some decision problems have efficient algorithms, like you said, for example, one of these odd cycle has, and so on. Right? Maybe we should go back and check how to do it. Decision problems for which an efficient algorithm is known. But is it clear what it means to say that an efficient algorithm is known? That should be like clear. These problems form a class which is called P. Okay. So the class P is a class of problems, computational problems, that have a yes-no answer for which we know an efficient algorithm. Right? So for example, GCD is in P. Okay. It's interesting to note that primes is in P. So this is a result by Raval. And it's a very hard result though. Not going to present it, but you should know that. It comes with much effort.
How does GCD come in decision problems?
Okay, yeah. So GCD is not. So at the moment GCD is not decision. That's right. I just erase it. Because I've defined it as class of, that is true. I should not write it here. GCD has an efficient algorithm, but you cannot really say that it's in P. Paste something. Okay, so this is something. Similarly, planarity also we know that it is in P. I'm not going to present these, but it's good to know that amongst the problems we saw, there are some problems for which efficient algorithms are known, and getting such efficient algorithms is like really useful. So this is a result by Hopcroft and Tarj. Okay, and some easy ones are maybe odd cycle in a graph, which you should go back and try. So now at least looking at satisfiability, one question is how is the input given to you? Maybe the input is given like this, let's say. A graph, right? It's more amenable to or x2, x3 or not x4. So this is how the input is given to you. When I said given phi, this is your phi. It's on 4 variables, x1, x2, x3, x4. Right? So now at the moment, at least if somebody gives me a formula and asks me to figure out whether it's satisfiable or not, I know that there are 2 to the n possibilities. Right? So I can plug in each of the 2 to the n possible assignments for these variables and then evaluate this formula bottom up. Right? Go through this AND gate, then this, OR gate and then AND gate, and see if the root evaluates to 1 or not, 1 by 1. Okay. So how long does that algorithm take? Right. So the size of this formula, how many ever gates are there in this formula, times 2 to the n. Right. So that algorithm is something like order 2 to the n. So I'm just going to write size of phi to represent the number of gates, right? The size of the graph, time algorithm. So I don't know how to make this better. Okay. At the moment, it's not clear. But one thing I know about this problem is that if you give me an assignment, A1 to AN, in 0, 1 to the n, I can immediately tell you whether this is a satisfying assignment or not. When I mean immediately, by investing polynomial amount of time, right, can decide. So let me call this A, okay, this whole vector can decide if A is. So I will just use a shorthand notation. If it's not clear, let me know. Is that okay? So I don't know how to solve it, but if somebody really comes up with a claim that look, here is the assignment, then I can figure out whether you are saying the truth or not, right, quickly. And I mean quickly in time polynomial in the size of the input. Okay, so that is something that this problem seems to have, right, satisfiability. So I don't know how to really figure out that assignment, but if somebody comes up with a claim, then I can find this out. So it looks really hard to find such an assignment. So what is it that this problem has? If the formula is satisfiable, right? If the formula is really satisfiable, I know that there is one satisfying assignment, right? And if you give me that assignment, I can verify quickly whether it's correct or not, right? If the formula is satisfiable, then there exists a proof that is verifiable, right? So some things to note here are that there exists, I don't know how to find it, but I know that one exists, right? Second thing is this proof is short. What do I mean by that? The length of the proof is only n, which is smaller compared to the size of the input. The formula has at least n variables. And I know that this proof can be efficiently verified. Right? So these three things are there.
Why does it have to be short?
Well, if you give me a very large proof, I do not even have time enough to read that proof. Right? So my aim is to, if I want to come up with efficient algorithms, right, even if I want to efficiently verify it, I should be first able to read the proof that you give me, right? If I cannot even read all the variables, I cannot set the variables. It's like that. Okay. So if the answer is indeed yes, if the input is a yes instance, then there exists a short proof that can be efficiently verified. Right? And if the formula is unsatisfiable, what can you say? So by unsatisfiable, I mean that there is no assignment that you can set so that the resulting thing will be 1.
Has no proof.
Then there is no proof, right? Then no such proof exists. The formula is not satisfiable, right? There is no such, okay, so when I mean proof, I should probably say that there is no such assignment. I am calling the assignment the proof, right? No such assignment that satisfies. I'm thinking of the assignment as a proof to the satisfiability of the given form. Okay? So if the answer is no, so this problem has this property, right? If the answer is yes, then there is an assignment to the variables such that I can efficiently verify it. If the answer is no, then there is no such assignment. And it's a decision problem that we are thinking of. So at the moment, we don't know how to solve this problem. So there can be decision problems that have this property. So decision problems where the yes instance, so decision problem means that every input instance is either a yes or a no. Right? There are only two possibilities. So the yes instance has a short certificate or proof or witness that is efficiently verifiable. And for no instance, no such certificate exists. I say certificate instead of proof. No such assignment. So problems that exhibit this property belong to the class NP. N stands for non-deterministic, We have not introduced non-determinism, but you can think about all decision problems that have this property, right? At least satisfiability definitely has this property. Maybe there are some other problems that have this property. Okay, so we have seen decision problems appears that some problems that we have listed are in the class P, some of them are in the class NP. Right? At least one of them is clearly satisfiabilities. So, what about composites? So, instead of primes, I am going to give you a number and you have to decide whether it is composite or not. So, satisfiability is in NP. What can you say about composites? If the number is composite, is there some proof that you can give me?
Yeah, we will divide, like some number will be a divisor.
You can provide the factors.
You can provide the factors, right? So, factor is a certificate. And once you give me the factorization, I have to just multiply, right? To check whether it's the actual number. I mean, I'm getting the actual number. So, composites is also in NP. Is that okay? Makes some sense, right? Okay, so if I look at problems for which there is an efficient algorithm and problems for which this property is true, right? So what does this mean? This means that there is an efficient algorithm, let's call this A, right? This algorithm. When I say efficiently verifiable, it means that there is an algorithm that can efficiently verify, right? When presented with the input and this short certificate, it will say yes or no. It will accept or reject. So, it's not very difficult to observe, but I'll write it anyway. That every decision problem in P is also in NP. So, if you can efficiently solve the problem, you can also efficiently verify. Does this make reasonable sense? So, now what about the other direction? If you can verify, does it mean that you can solve? Is it a no or is it a maybe?
We don't know, it's not necessary.
It's not necessary, right? So,
We don't know.
this is not known. Yeah, these two clauses the same. In principle, we are asking, is every problem in NP also contained in P? In one direction is known, right? The other direction is what you have to solve. Okay, so there are some problems which we haven't yet seen, right? Amongst the list of problems that we did. So let's try something else. Okay, so suppose satisfiability is in P. Let's take a minute to do that. Suppose satisfiability is indeed in P. Suppose, I should write suppose. This means that I have an algorithm that given a Boolean formula can efficiently tell me whether the formula is satisfiable or not. Can I get the satisfying assignment? But searching seemed harder, right? I thought that when we wrote the list of problems, felt like searching for an assignment should be harder than just saying whether it is. Maybe you can quickly figure out whether it is satisfiable or not. Why should you be able to search for the assignment? Can you do that? So one thing to note is if P is unsatisfied. So I know that satisfiability is in P. So there is an algorithm, right? That on input phi will efficiently immediately tell me whether the formula is satisfiable or not. So let's call that algorithm A. Right? So if phi is really unsatisfiable, that is I supply phi to A and it says no, then I cannot find such an assignment, right? So you just say no. Suppose it says yes, right? This algorithm says yes, indeed, it is satisfiable. So it's a formula on n variables, x1 to xn. So what can you say? What are the possible values for x1? 0 or 1. I have with me an algorithm that if I give it a formula, it will tell me whether that is satisfiable or not.
So you can just try 0 or 1 for the first variable and then it reduces to n minus 1 variables. So
Right,
you just check if
exactly.
the rest is satisfied.
Right? So if this is yes, then so for all I can do this. For every I in 1 to n, I'll ask if A of phi by setting, maybe let's start with x1, right? So x1 is equal to 0 to xn. Is this satisfiable? Right? If this says yes, the algorithm just returns yes. I know that x1 should be 1, should be set to 1, right? Else x1 should be set to 0. I have to do this for every I. I mean, these variables will be x minus. Right? So by asking this algorithm repeatedly, you can get that satisfying assignment. What's the problem?
Shouldn't that be 0? X1 equals 0.
This.
Else x1 equals 1.
Yes. So maybe, yeah, that's right. So a1 equal to 0, else a1 equal to 1. How do you erase it here? Yeah, that's right. Thanks for spotting. So I do this and then output the assignment. A1 to an. Right? That will be a satisfying assignment. Is that okay?
But doesn't that again make it non-polynomial because that will be 2 to the power n?
No,
You
it's
just
not
check
right.
every one.
So I have an algorithm at my disposal, A. I have made n plus 1 calls to this algorithm. If that algorithm was efficient, I'm not incurring more time, right? But it is based on the assumption that there is an efficient algorithm for P, right? So at least for satisfiability, if I can decide, I can search. Right? Satisfiability has this additional property. So a priori, it looked like searching was harder than decision, which it really is not, but it heavily relies on the fact that this problem is satisfiability. Right? Every variable is either 0 or 1. Okay, so that's an observation. So let's go to slightly different problem, which is max cut in a graph. So you're given a graph G without loops. So at the moment, let's say without loops. Was the question clear? You had to find an S and a T subset of V such that the size of the cut, right, which is the cardinality of edges V, is maximized. So what would be a first algorithm to do to solve this problem?
Brute force.
Brute force. So what is that brute force algorithm? Just try to partition, right? But that requires a lot of time, right? A lot of steps. So I don't know how to do this efficiently. So suppose I give you additionally a coin, right? It's a fair coin and it has two sides, head, tail. And you are allowed to toss this coin a few number of times, as many number of times as you want, let's say. So you are given a graph G, right? It has some n vertices. Okay, so let's say the vertex set of G is V1 to Vn. And you are allowed to toss a coin. And you have to produce a set S and its complement. It's a partition of the variable set. So one is S, the other is everything else minus S. Is there something that you can do? And what's the first thing you would try?
Every vertex toss the coin to get heads, put it into.
Okay, so let's do that. So toss the coin for every vertex V in if heads, V is an S, else this V is this, V minus S. It's a simple algorithm. I've tossed the coin n times. Okay, right? So now Now if I analyze this quantity, now I have an S and a T, right? So my T is V minus S. These two sets are there. But this algorithm additionally has this capability of tossing coins. I give you a coin. So what can you say about the size of the cut? I cannot really say size of the cut. So I'll just put cut of S, okay? So there is S and V minus S, and then there are edges going. So what can I say about this quantity? The expected size of the cut. You are familiar with expectation, right?
It's n by 2.
Okay, so what is, okay, so maybe I should write it, and then what you said is correct. So for each edge in E, what is the probability that E is in the cut? Is it clear? You will get like 1 by 4 plus 1 by 4 times mod E. I suppose this is clear. If it's not clear, please ask, okay? Does that make sense so far? So you did not, okay, so the first thing to observe here, which I missed to say, is that max cut is NP hard. Okay, so I presume that you have been introduced to NP hardness in one of the previous lectures. So it's a hard problem. Okay. So I'm not expecting that there will be an easy solution for this problem. But there is an easy solution that sort of gives you some cut, right? So how large can the max cut actually be in any graph? Probably the star graph that we saw, this one. So this one has a cut where, I mean, this one has a possibility where everything, this was in S and this lone vertex is in T. The number of edges is actually the number of edges in the cut, the max cut value is exactly the number of edges. So how large can it be? Why is it n minus 1? So n is the number of vertices. You said m, is it?
N.
Oh, here, okay, in a star graph, but in a general graph, right, given like a set of vertices and number of edges, right? That's okay. So this value is, oh, it's the other way around. Yeah. It's the optimum cut, I mean the maximum that you could ever get by 2. It's at least that much. And you did not really do much, right? I mean, you just tossed some coins. And you got away almost with a good solution. It's not a bad solution. It's at least half of the actual value, right? Probably much more if you get lucky, right? But what did this algorithm do? It has the ability to toss some coins. So you really did not know how to solve this decision problem. I mean, not decision problem, but this optimization problem without coins. But given coins, there is a simple solution that can do reasonably well, right? But this algorithm is an example of a randomized algorithm. So what is a randomized algorithm? It's like any other algorithm. It has an input. Of course, you need to produce an output, possibly yes, no. Right? Additionally, this algorithm has some random coins at its disposal. You cannot use many, right? If I want an efficient algorithm, then I can use many such random tosses. I mean, it should be bounded by the running time of the algorithm. Now, what is it that makes this different from probably your other algorithms that you saw earlier for primes 1 to root n? What is one thing that is different here? It could be wrong, right? So there could be errors. There is something else, it's probably like very important. So you came up with an algorithm to find primality. It was bad, it's okay, it was root n. So if I give 3 to this algorithm, it should say prime, in whatever algorithm you design. If I give 5, it will say prime. If I give 3 again, what will it say? It will say prime.
It doesn't behave like a function.
Right, so now if I give the same input 2 times to the same algorithm, it will produce, it could produce different answers, right? So the behavior of the algorithm is not the same on the same input itself, right? So same input given, I mean, several times, could produce different answers. Right? Okay, so that's what a randomized algorithm is. Maybe there is something else there. Okay, so here is a problem you saw in the previous lecture. Let me describe the problem. Okay, so suppose I give you a decision problem, okay, something like polynomial identity testing. This was introduced in the previous lecture, right? Suppose there's some decision problem and I ask you to come up with an algorithm that is correct with probability exactly half. What will you do? Sorry?
Run it a bunch of
No, just probability half. No, what do you mean by run it? This is a decision problem. I'm asking you to come up with an algorithm that succeeds with probability half. So it will give me the right answer. If the input is actually prime, it should give me yes with probability half. If the input is composite, it should give me no with probability. Sorry?
If it comes up heads, then say yes, and otherwise say no.
Just don't even solve the problem. Toss a coin. If it says yes, say prime. If it says no, say composite. It's correct with probability half.
but like primes are less common.
Yeah. Shouldn't it
Why
depend on
should
your density?
So what I meant is, given any decision problem, there is an algorithm which is randomized, which is correct with probability exactly half.
No, but in this case, the density of primes is not half, right? Then how is this probability half? Like, why aren't we considering the density of primes in the natural numbers?
That's because I should not have said primes. Yeah, given any decision problem.
Even odd testing, we can say like.
Yeah, you don't even have to really look at the problem I'm saying. It does not matter what problem you're going to solve, just toss the coin and give me an answer. Right?
Like doesn't really depend on the density, right? Basically, if you are given a number and if it is prime, then it says yes half the
How
time.
about this? I tell you, if this is a decision problem that it doesn't leave remainder 1 and divided by 3. So if you want to be correct, you should output something like 1/3, right?
Exactly, that's what I was going to.
You should not output half everywhere.
So that also depends on whether you are getting all the inputs equal
Uniform.
and
Equal.
Yeah.
That's
what
like
you're saying is I
assumption.
could keep on asking you the same number and you keep tossing a
And
coin
you
and
correct
50% of the time you get it right. Right? So you're not promising that the inputs are also coming with the same distribution as the
Yeah,
programs.
but you cannot also assume otherwise, right?
No, in the problem, basically, you are not told that you will be asked different inputs. Like for any input, well, it will be correct half of the time. Like if you provide the same input multiple times.
Yeah, but if you account
Okay,
for
for the same
density
input.
Yeah, for the same input. Like we are discussing the same input.
I didn't understand.
What you didn't understand, you should probably say.
Like
So is this statement okay? Given a decision problem, there is an algorithm, right, that is always correct with probability half. Exactly half.
For a particular input, it's always half.
Yeah, for a particular.
okay, yeah.
If you take
Yeah.
5,
Yeah.
it might be prime, it might be not.
Yeah, okay.
There are only two possible answers, you toss the coin.
If you
So
apply to
anything,
the
yeah, if you want to say anything influential, you should say something that's greater than half, right? I mean, anybody sane would try to design an algorithm that succeeds with probability strictly greater than half. That's what I was going to say. Okay. So this, I suppose you have already seen this problem. So can you define the problem?
If
Or-
you are given polynomials p and q,
Okay.
Like
Okay, sure.
show p minus q is 0, or show like it's a decision problem that is p equal to q, p minus q equal to 0.
So I'm using this notation. I suppose you have been introduced. It's equal to 0, identically 0, right? It's like, okay. So I'm going to use something that was, so let's just give one polynomial, okay? So given a polynomial p on x1 to xn, n variables, degree d, right? Decide if p is identically 0. Yeah, I'm considering p minus q as my input. So in principle, if I give plus b whole square minus a square minus, I should answer yes. This should be no. Okay. Okay. So I'm going to use something that you saw in the last lecture. So I suppose you have seen that if you evaluate it at a random point, the probability is non-zero is high. I'm going to trust that you have already understood this. Schwarzschild. Were the names introduced?
Yeah.
Okay. So this is. So what does this say? You are given a C, let's say P x1 to xn, correct? And whatever degree D, so on. And I'm going to toss coins, or I'm going to like pick uniformly at random from 1 to let's say 3D. I think 2D is also sufficient. Then the probability that if I pick such an R and evaluate my polynomial at R1 to Rn, 0. I don't know what was done. Maybe half was done.
We had D over size of S, and in this case the size of
Yeah,
S
it's
is
3D.
So, yeah,
So you probably saw D by mod S, and mod S here is 3D.
we didn't take a specific value for S.
Okay, but I have fixed this just to make it clear. I mean, it has no additional notation. Okay, so you are given a polynomial of degree D. If I pick a random point from this set, which is reasonably large compared to the degree, then the probability that the chosen point is actually a root is small. Does this make sense? Like whatever is written. So, see, if the polynomial is identically 0, no matter what point you evaluate, you will get 0. But if the polynomial is not identically 0, the only unlucky case is probably you actually hit the roots. Right? But what this is saying, if the grid is reasonably large enough, then the probability with which you will land up in a root, if you pick the points uniformly at random, is reasonably small. All reasonably quote unquote, I have substituted. Is that okay? Okay, so now so here is the input. The input is given as a polynomial. So you might want to ask how it is given. So just like a Boolean circuit, maybe it's given like this, with a bunch of multiplication and addition gates. And the degree, let's say you are promised D. So now can you come up with an algorithm? Or does this give an algorithm? This statement here.
You can just repeat it multiple times.
Yeah, but let's not even repeat it. You can do it just once, and what will you get? So let's say if P is identically 0, what is the probability with which, so what the algorithm does, it picks points from this uniformly at random and is going to substitute, right? So substitution will not take much time, meaning you have to again evaluate this tree bottom up, right? So it will be size of this, whatever, if this is represented by some graph C, then size of this, right? So this is an algorithm, right? You pick the point uniformly at random and then substitute and check, right? So what is the probability that your algorithm will say, yes, it is identically 0? If the input polynomial is actually identically 0. Sorry? 1, right? So if it's not identically 0, that your algorithm will say no. Okay, maybe I should say yes, but I'm going to say no. 2 by 3. Or I could have even said algorithm is yes with probability at most 1/3. So this algorithm, I mean I have not written the algorithm, but I suppose the algorithm is clear. Right? So this is a probabilistic algorithm. Right? It has some random coins with itself. It's going to toss, and it's also polynomial time. Meaning the only thing you had to do was evaluate it at this point, which is like polynomial in the size of its input. Okay. So now one thing to observe, whatever he said, was probably you can repeat this algorithm and try to reduce the error. If I repeat this many times, the probability that with which bad things will happen again and again and again keeps getting lower and lower. Right? So now that brings us to another class. So we want to look at decision problems for which there is a probabilistic polynomial time algorithm, right, such that on all inputs x, right, if, okay, I should have written x, so x, if x is actually a yes instance, so x is an input and it's either a yes instance or a no instance, right? If the input is actually an yes instance, let's call this algorithm A. The probability that A outputs yes is at least 2/3. With reasonably good probability, you should say it is yes. If it is a no instance, the probability with which A outputs yes, almost 1/3. This seems like a reasonable requirement, right? Something good. So this is called the class BPP. So all problems, decision problems for which such an algorithm is known. Right? So this is bounded error. The error is bounded by a constant. This is probabilistic. The algorithm has some probabilistic feature, polynomial time. So suppose the problem is in P, then there is an efficient algorithm for it. Right? What does that mean? This means that there is an algorithm A that does not use any random coins, and if it's a yes instance, it will say yes with probability 1. And if it is a no instance, it will say yes with probability 0. So what can you say about P and BPP?
PPP is inside. PPP would be inside P, like subset of
I didn't get why that would be true. So because it's greater than 2/3, how can you say it's greater than or equal to, I mean it's equal to 1? Yeah, so if a problem is in P,
P. Yeah, it would be in PPP.
exactly, so this should be the thing, right?
Oh, sorry. Yeah, I said.
Okay, so does that make like some sense? So now the next question is, so is randomness really powerful, right? If I come up with an algorithm that is randomized and succeeds with reasonably good probability, can I just suck the randomness out of it and produce another algorithm that just decides the answer without using any random coins? So that's not known. Okay, so now you may want to go back and look at some of them and try like randomized algorithms for these, maybe even for satisfiability and so on. So there are efficient, the nice thing about randomized algorithms is there are simple algorithms that are efficient that provide reasonably good answer. If I am okay with compromising on the optimality, then here is a very simple algorithm that uses randomness. And this also shows that, okay, see that PIT is in BPP, or maybe, is that okay? So, yeah, I wanted to do something more, but maybe we should stop, right? It's
Is
okay.
the 2/3, 1/3 just like no
Can,
theory behind it, or just a random choice?
no, it's not a random choice.
Like why not something like 5, 6, and 1/6?
Some good enough constant probability. But if you have 2/3, 1/3, can you not just repeat it and get whatever you
Yeah,
want?
that's what I said. Like
Yeah.
why not anything? Why does it work?
Yeah, for every c you can make it whatever, 1/2 to the c and 1 minus 1/2 to the c. I just made it 2/3, 1/3 because you saw Schwarzschild for which it was 1/3. Right? I mean, it's easier to write. Yeah, the most general thing would be that for it. I mean, if you have this property, you can get whatever property that you are saying. Right? This is the simplest to write on this. Okay, so maybe let's stop.